Hello guys, my name is Amit. So today we are going to discuss this problem, number of ways to reorder array to get same BST. Okay, so the question is given that given an array of nums that represent permutation of integer from 1 to n, we are going to construct a binary search tree, inserting element of nums in order into a initially empty BST. So we have to find the different number of ways to reorder nums so that we can construct the identical BST. Okay, so let's understand the problem. So let's understand from this example. So we have um, a input array as 3, 4, 5, 1, 2, and we have created a binary search tree here. So we know the property of binary search tree is that all the elements on the left of a node are lesser than the root node. All the elements on right are greater than the root node, and it applies to all the nodes. So for example, this is the root node 3. All the elements on the left, that is 1 and 2, are less than 3. All elements on right are greater than 3, that is 4 and 5. For node 4, all elements on right are greater, that is 5 is greater than 4. Here, it cannot come any element, but we'll take an example where we'll have the left subtree of this intermediate node. Okay, so how we have constructed this BST? So first we have, okay, let me move to here. Okay, so this is the input array. So to construct a binary search tree, what we are doing here is we have taken 3 here, then we have taken 4 here, since 4 is greater than 3. Then we have the element 5. So we'll check that 5 is greater than 3, yes. 5 is greater than 4, yes. So it will be inserted at right of the 4. Then we'll have the element as 1. So we'll check whether 1 is smaller than 3, yes. So we'll insert it here. Then we have the element 2. So we'll start from root node. The element 2 is smaller than 3, yes. Element 2 is greater than 1, so it will go on to the right of node of 1. So this is our BST. So we have to, so this is one input combination which generates this BST. So question says is that we have to find all other combinations, these combinations, which actually generate the same BST. So BST should be exactly same. So let's see how this combination, that is 3, 1, 2, 4, 5, generates the same BST. So root node is always fixed. So we'll take 3. Then we'll have 1. So we'll check whether 1 is greater than 3 or less than 3. Less than 3, it will go on the left. Then we are on 2. So from 3, we'll have 2 less. For 1, 2 is greater. So we'll insert 2 here. Then for 4, we'll have 4 is greater than 3. We'll insert it here. This is 4. And for 5, we'll start from root. 5 is greater than 3, 5 is greater than 4, so we'll insert it 5 here. So again, if we can see, these two trees are exactly same. So let's take one more example, this one here, 3, 4, 5, 1, 2. Okay, so we'll insert the root node 3, then we'll have 4, which comes on to the right. Then we have 1, which comes on to the left. Then we have 5, so we'll check 5 is greater than 3, 5 is greater than 4, so it comes here. And then we have last 2, so 2 is less than 3, 2 is greater than 1, so it will come here. So all these 3 trees are equivalent, that is exactly same. So these 5 arrangements, that is these 5 arrangements are also, let me say this way, these 5 arrangements form the exact same binary search tree which is formed by this input uh, array or the input arrangement. So the answer is 5. Right. So this is basically the question. What the question says is. Okay, let's move back to the question again. So what other things it says? For example, the given number 213 will have 2 as a root, 1 is left, 3 is right. The arrangement 213 also yields the same BST, 321 yields the different BST. Return number of ways to reorder nums such that BST is identical and we have to return in, the answer may be very large, we have to return in modulo 10 raised to power 9 plus 7. Okay, so this is one thing. Now let me, okay, so provided our BST, so there are few preconditions which we should note. So the first precondition here is, first is root node is always at index 0. So in all the arrangements, if we see, root node is 3 and it is always at index 0. Second comes the relative positioning. So you'll see many solutions, they talk about the relative positioning of elements. Should be same. So what does this mean? This means that the elements which are there on the left subtree of the root node, which is 1 and 2, and elements which are there on the right subtree of the root node, which is 4 and 5, should have the same relative position. It means what? That 1 should always happen or occur in the array before 2. So as if we can see here, 1, so if you can see here, 1 is before 2, 1 is before 2, 1 is before 2, 1 before 2, 1 before 2, and 1 before 2. And similarly, um, on the right hand side, 4 should be before 5 in all the arrays. If we see here, all the positions, otherwise what will happen? We will not have the same binary search tree. So first is root should be at index 0, or root will always be at index 0. Second is relative positioning, pardon me for the spelling, positioning of left and right should be same. And third is, we'll check that we have to use the recursion or the depth first search here. We'll see why while we move ahead. So since we have to find all the combinations, so we'll be using our combination formula. So if you are not aware about the combination formula, let me show you how the combination formula works. So we have a combination something as n c r, it's equal to n factorial divided by r factorial into n minus r factorial. This is our combination formula which we'll be using. So it means what? Out of n places, we have to choose two elements or two elements to be placed, and they cannot be used interchangeably. So for example, if we see here, for the left elements, that is left 1 and 2, these are the two elements. So in this case, our r will become 2. And if we see here, if we see these positions, okay, let me go back to the brush again. If we see these positions, let me put a blank for the position of 1 and 2, 4 and 5, this one, right? And it will be 3, blank 4, 2 and 5. Then for this one, it will be 3, blank 4, 5 and dash. Then 3, 4, dash dash and 5. Then 3, 4, dash 5 and 2, right? So if we see here, we always have the two positions which the left sub elements or the left tree or the elements in the left tree can fill. So here r becomes 2, and we have in all total 4 positions. Why 4? Because the root element is always fixed and it will always occupy the first place. So we'll have four positions. So our combination will become 4C2. This is the number of ways we can arrange the left elements in the left element. So it will become 6, right? Because it will become 4 factorial divided by 2 factorial into 2 factorial. So it will become 4 into 3 divided by 2, right? Because 2 factorial cancels. It will be 2, so it will become 6. So if we can see here, there are 6 positions: 1, 2, 3, 4, 5, and 6. And the final answer will be less 1 because the input is already taken and we have to exclude the other ways, other BSTs. So the answer will be 6 minus 1, which will be 5. But now the point here is we can have other trees as well, which can have left heavy tree. For example, let me delete this. Instead of this tree, we can have some tree as 100, and on the left we can have 50. Then we can have 25 here. Then on the right we can have 75, and then we can have 10 here, and we can have 20 here. Right, and on the right hand side we can have 150, and we can have some other numbers, maybe 200 and 150, less than 150, 125, right? So here what will happen is the number of elements on the left subtree is 4. Number of the elements on the right subtree is 1, 2, 3, 4, 5. 5 is 5. This is 5, pardon me. And number of elements on the right subtree is 3. So the combination for the left subtree will be how much total number of elements are: 1, 2, 3, 4, 5, 6, 7, 8, 9. So total is 9, out of which we have to take 8 positions. For left it will be 8C, 1, 2, 3, 4, 5, 5. And for right it will be 8C3, right? We from 8 positions we have to place on 8 positions we have to place 3 elements, and then we have to sum up these two things. But the again point here is we have to use the recursion here, uh, because in this left subtree, if we can see these elements, that is 25, 10, and 20, that is the left subtree elements, can also be arranged similar to there in the whole subtree. That is, for example, we have a simple um, a tree, for example, 3, 1, 2, 4, 5, where 1 and 2 and 4 and 5 can take only 4 positions. That is, 1 should always be before 2 and 4 should always be before 5. But if we have a bigger tree, then we'll have more combinations. So this bigger tree will have one combination. Inside that, it will have different combinations. So we'll have to perform a depth first search where we have to iteratively go inside every tree. We have to calculate all the combinations inside every tree, and then we have to return the answer. Okay, so until now we have taken, okay, so we have noted that root will be at index 0. Second, relative positioning should be maintained. And then we have to use depth first search recursion to find combinations inside tree, or in subtree, right? So that's it. So now there is one concept of Pascal's triangle. So let me tell you what it is, because it will be very helpful. So Pascal triangle is a triangle which actually stores all. Okay. So Pascal triangle is a triangle which stores all the combination tree. For example, let us take an example of a Pascal triangle of we have something, we'll take a row, something as this. We'll take a 2D array. So this is 0, 1, 2, 3, 4, 0, 1, 2, 3, and 4, right? So in Pascal triangle, we have all the first column is always 1. All the diagonal elements are always 1. Okay. Now what will happen? If you want to calculate this element is 2, 1, so it will be sum of these two, this and this, so it will be 2. Now if you want to calculate 3, 1, so it will be sum of these two elements, so it will be again 3. If you want to calculate 3, 2, so it will be sum of these two elements, so it will be 2 plus 1, which will it will become 3. Now similarly 4, 2, so 4, 1, sorry, 4, 1, this element will be sum of the above two elements, so it will be 4. Then this one, this element will be 6, which is sum of these two elements, this and this. And if we want to calculate 4, 3, so it will be 3 plus 1, which is 4. So it will be sum of 3 and 4, right? 3 and 1. Okay. So this is a Pascal's triangle. So how this is useful to us? So if we see, if we want to calculate NCR, where um, N is equal to 4, CR is equal to 3. Okay, so we need to calculate 4C3. So what's the 4C3? 4C3 will be equal to 4 factorial. Let me calculate it. 4 factorial divided by 3 factorial into 1 factorial. So it will be equal to 4. And if we see here, 4, we'll take this 4C3. This will be R, and this will be N. So this will be R, this whole row will be R, and this will be N. So this will be 4C3. So it will be 4. So this is a correct answer. Now let's go to 4C2. How we are going to calculate 4C2? So it will be 4 factorial divided by 2 factorial into 2 factorial. So it will be 4 into 3 into 2 factorial, which will cancel out. We'll cancel this, and this will become 2. So it will be 2 into 3, 6. So this is again the correct answer here, right? 4C2, this is also correct. So we'll store the all the combinations in the Pascal triangle, and while using a DFS or recursion, inside while using the recursion, we'll just find the element and we'll calculate the answer. Okay, so let's move on to the actual question, actual code here. Okay, so here we have the input array, that is nums. So also note, it's told in the question that the number of nums length, that is number of elements, is less than 1000, and value of element is also less than or equal to 1000, right? So we can have up from 1 to 3 and so on up to 1000. So we have taken a two-dimensional array, that is two-dimensional vector, this one, and we have taken it as 1001 because it starts from 1, so we'll ignore 0. So we have taken from 1 to 1001. This is, we say, Pascal triangle, and we have initialized the Pascal triangle using the same formula which we have seen earlier. So from 1 to n, we have initialized the Pascal triangle. So now the Pascal triangle will contain all the combinations, and we have taken it as a mod because otherwise it will become very large quantity. Then we will move into the depth first search function. So here in the depth first search function, if the size of the input array is smaller than 2, then we have to return 1, because for 1 and 2 there is only one combination, that is 1 always happens before 2. So we'll return 1. Otherwise, we'll find the elements, number of elements which are in the left and the right sub tree. So if element is smaller than the root node, then it's in left subtree, otherwise it's in right subtree. Then we will find the left combination using depth first search, and we'll do it left. That is number of we'll go to the left subarray, we'll go to the right subarray, and here is the combination calculation. So combination we are calculating as n minus 1, that is on Pascal triangle size minus 1, size is the input array, and the left elements, number of the elements on the left. So that's what, right, we have seen here. So if you remember earlier what we have seen, uh, for 1 and 2, 1 and 2, we will have the formula of 4C2, right? Because we'll have 3 dash dash 4 and 5, then we'll have 3 dash 4 dash and 5, and then we'll have 3 dash 4 5 and 2, 4 5 and dash here, and then we'll have 3 4 dash dash and 5, and 3 4 dash 5 and dash. So here we have this formula, that is the for calculating all the combinations of the left elements is the number of elements on the left, which is 2, and the size of array minus 1, right? So this is what we are doing here, size of array minus 1 and number of elements on the left subarray, right? So this is the combination which similar to as 4C2 we have calculated here for the left subarray, and multiplied by the left combination, and then we are doing mod because the output should not become too large, and then we are multiplying it with right combination, because if we note here, we are not adding it, we are multiplying it, because in combinations we have to multiply it because it's a factorial, so we'll multiply it, and then finally we'll do a mod of the output, and the output will be minus 1 of the output returned by all the combinations. So this DFS will return all the possible ways where the left subtree maintaining the relative positioning of the elements will have all the elements, right subtree maintaining the relative positioning, all the different combinations on the right subtree, and we, because we have taken one uh, combination already as an input, so the output will be returning minus 1. So that's the logic out of it. Thanks a lot. Have a good day.